Okay, so I started this new section. It was called conditional probability. We were talking about finding probability, but not just regular probabilities. Finding a probability knowing that something else is true. So for example, we did this example where we figured out, okay, what's the probability that I have a disease, knowing that I already tested positive for the disease? And as we figured out with this activity, is that conditional probability, it's really hard to figure out these probabilities because it's not very intuitive. Like you can't just look at a problem and just know what the probability is. You have to do a little bit more work. So what I did is I figured out the best way to solve these problems is just creating a chart. Creating a table makes it so much easier to be able to figure out these probabilities instead of just like figuring out in your head. So what we did is first I gave you a formula. Okay, so whenever you're asked to find the conditional probability of something, and Sarah, do you have these notes? Yeah, all right. Here you go. And what I said is, okay, let's say we have two things. So let's say I want to find the probability something called big E. Okay, so for example, having the disease. And I already know that this other event, which I call K, is true. So I want to know the probability of having the disease, given that I already know I tested positive. We call this conditional probability. We label it the probability of E with a line through it and K. This line is basically like the given symbol. It just means we're dealing with a conditional probability question. And our formula is the number on top is going to be where both E and K are true. And the number on the bottom is where just K is true. So we basically count the number of things where both of them are true and put it over counting the number of things where just the given thing is true. Okay, we did a couple examples with these things called two-way tables, where we just had to figure out, okay, what number went on top and what number went on the bottom. We were able to figure out these questions pretty easily, but then I told you that, okay, these aren't, gosh, these don't have to be two-way tables. They can be three or four-way tables. They can be more than just two in each category. So what we're going to do today is we're going to kind of expand on this idea and move into examples where we don't have just two things in each category. Okay, it works pretty much the same, but we're just doing more things. Okay, so in this example, it says we have a survey. This survey is done on the commuter, so people who drive or like take the train or walk to three major cities. They're asked how they go to work, and then they also ask, okay, what cities did you go to? So here we have a different table. It's not a two-way table, but it has different categories, works about the same. I think it'd be a good review for us to just go on and figure out how we figure out or how we fill out the table. Okay, so take a look at the cell, oh, bless you, on the very right here. This represents a total. What is this the total of? New York, right? Because if I take this total, this represents if I add up everything across the rows. So basically to fill out this table or to fill out that cell, you just add the 10, the 50, and the 20. And did you get that one? It's 80. Perfect. I am not good at adding in my head. That's why I have you guys. And that number represents the total number of people who live in New York. Okay. Then you can go through and fill out the other ones, right? Adding across, we get 70. Adding across, we get 50. And those tell us how many people live in LA and how many people live in Chicago. Okay. Going down to the bottom rows, these rows actually tell us, okay, how many people take the car, right? Instead of looking across, we go down. So in order to fill out that row, we just multiply, or sorry, add down 10 plus 36 plus 16 gives me 62. Okay. Adding down gives me 102. Adding down gives me 36. And that tells us how many people take the car, take the train, and how many people walk. Okay. The final one is the row on, or sorry, the cell on the very bottom corner there. How would I figure out how to get that number? add down or across, right? So it actually, there's two ways to be able to figure out that bottom cell. You can either add down and like do 80 plus 70 plus 50, and that will give you 200. Or another way you can do it is add across, and that would also give you 200. What I like to do is I like to do both, add down and add across. And if those two numbers match, then you know that you did the chart right. Okay. Any questions on filling out the chart? Perfect. Okay. So what I've done is I've listed some questions here, and I think maybe we should just go through them together. So I know it's been a while since spring break. Let's just go through these questions together, and then I'll give you a chance to work on these on your own. So let's do part A. This is asking me the probability that I don't know anything about the situation. All I know is what's the probability that if I rounded up every single person in this entire sample and I select a person, what's the probability that that person's going to be from New York? Well, this isn't using the formula that I gave. This is just a normal probability. What number do you think is going to go on the bottom? The total of what? Yeah, the whole total, right? Because this question's saying, okay, what if I rounded up every single person in this entire group and selected one person, right? So the number on the bottom is going to be the grand total. And that's going to be 200. Okay. Then, of course, the number of the top, well, I need to figure out how many people live in New York, right? So the number on top is going to be how many people live in New York and how many people do live in New York. 80, right? So what I find a lot of people making mistakes on like tests and stuff is they'll see a chart like this and they'll be like, oh, the total number of people living in New York is 10, right? Because it's right next to New York. That's not the total people in New York. You have to go all the way across the row to figure out how many people total are in New York. So the total New York is 80. And in these questions, I don't really expect you to simplify the fraction. I think it's easier to just look at this fraction and be like, oh, that's how I get the answer. So you can, of course, simplify it if you want, but I don't really care. I just leave it like this. Okay. Let's move on. In part B, this one's asking me, okay, what's the probability that I select someone out of the entire total and they are both from New York and they drive a car? Okay. What number is going to go on the bottom? Mhm. Mm. Well, this question saying, okay, it's just asking the probability that I select one person and they're both from New York and they drive a car. If I were to do an experiment and figure this out, I think I would have to take everyone in the whole sample, right? I would have to round up the entire total 200 people to select that person. So what do you think is going to be on the bottom? 200, right? The grand total still stays on the bottom. Okay, so 200 still is on the bottom here. Really, the only way that bottom number is not going to be 200 is when we get to these conditional probabilities down here. Whenever we're trying to find like a regular probability that says and, or just like a normal one thing probability, that number on the bottom is just going to always be the grand total. Finally, if I want to find the probability of New York and car, well, I need to figure out how many people drive a car and are from New York. Well, it looks like that's got to be the number 10. So 10 is going to go on top. New York and car. Perfect. All right, going on to part C, this one is looking a little bit more conditional, right? I know that this is a conditional probability because we have that line in the center. Whenever there's a line there, I know this is a conditional probability question. So what this question is really asking is, what's the probability that I select someone who goes on the train, but I already know that they're from New York. So I don't really care about people who aren't from New York because I know this person is from New York. So let's just take a look at how we set up this. Okay, taking a look at my formula, I know that E represents the first one and K represents the second event. So if I go back to my formula, I know that E and K go on top and just K goes on the bottom. Okay, so let me just write this as a note. So E and K goes on top. I know that K goes on the bottom. Okay. Well, why don't we go ahead and fill out that bottom number real quick? I know that the bottom number is where just K is true or the second event is true. Well, K is really New York, right? So that bottom number has to be the total number of people in New York, right? Well, how many people are in New York? 80, perfect. So 80 goes on the bottom. Oh, did not mean to erase that. Oop, here we go. The number on top is where both E and K are true. So in terms of our question, we're looking for people who ride the train and are from New York. How many people are in New York and ride the train? 50, good, right? Because, well, that's where the cell is at. So this probability is 50 out of 80. So conditional probability, it's not very intuitive, but if we use our formula, all you need to know is where they both happen goes on top and the second event goes on the bottom. All right, any questions so far? Moving on, part D is like, okay, I want to find the probability of the train, given that I already know this person's from LA. So I don't care about anyone who's not from LA. I just want to know if I rounded up everyone in LA, what's the probability that that person takes the train? Okay, so let's fill out this one. What am I looking for on the bottom? K's on the bottom, and what's K this time? LA, right? LA is the second event. That's what I'm looking for on the bottom. How many people are from LA? 70, perfect. So that's the total number of people in LA. And then the number on top is, well, where both of them happen, right? So how many people take the train and are from LA? 24, perfect. Oop, meant to write that with my actual pencil. All right, so that's how we go about conditional probabilities. Once you know like exactly how to set up the problem using the chart and also like how to fill out each of these situations or on the top and the bottom, it's actually pretty easy to figure out these probabilities. Okay, the bottom one, I don't know why I put this on here, but let's just do it. If I want to find the probability of the train and LA, this is not a conditional probability question anymore because there's no line in the center. So that means, what do you think is going to be that bottom number? 200, right? It's always 200 or the grand total if there's no conditional probability thing. So this is always going to be the grand total or 200. And then the number on top is just where they both happen. So the train and LA, we actually said that was 24 in the last question. So this probability is 24 out of 200. So basically the difference between conditional and regular probability is that bottom number, right? We're kind of deselecting people from the entire sample when we do conditional probability. All right. Any questions on example number 3? All righty. Then if you flip the page over, I have another situation. This one's asking if people like bowling, going to the mall, or dancing. I'm going to give you a few moments to work on this example and we'll come back. Let's come back up to the front here. So I really like this example. We have a different type of table this time. In each row, in each column, we have 3 things going across and 2 things going down. Okay, so I like how Emma wrote down or filled out the chart. I think we were all on the same page here. So I like how she added across, added down. The only thing that I've seen mistakes on like throughout me teaching this class is when we write out the grand total, I feel like a lot of people like add up every single one of the total numbers. That's not how you want to do it. You can either add down or add across, but don't do both together. So make sure that you're just doing one of those. So you should have gotten 44 there. Nice job, Emma. Okay, let's keep going on. Part A, I got Michael to write up part A. Do you want to take us through how you got this answer?
Yeah, just look at the total number of people.
Mhm.
Bowling, put that over the grand total.
Awesome, right? So grand total always goes on the bottom if it's not conditional. Nice job, Michael. Moving on to part B, we wanted to find, okay, what's the probability that someone likes bowling and likes TV? And that was that Alicia? Do you want to take us through this one?
Bowling and TV can be decided through.
Perfect. So it was the both over the total. Awesome. All right, moving on to part C, we wanted to find the probability. Oh, this is a conditional one, right? Because there's a line in the middle. So that means we have to actually follow that formula. Gabrielle, you took this one, right?
Yeah,
Do you want to take us through this one?
it was both bowling and TV over just TV.
Perfect, right? So both over just TV. Nice job there. Any questions so far? All right, part D was like, okay, I want to find the probability that someone likes dancing given that they already like movies. So I don't care about people who don't like movies. I just care about the people who like movies. This one was, Lauren, do you want to take us through this one? Perfect. Nice job there. And then part E was, okay, I want to find the probability. I actually switched up part D and I just switched the two here. So this time I'm only interested in the people who like dancing and I want to find the probability that they like movies. Hunter, you want to take us through this one?
It's just the people that like movies and dancing over the total people that like dancing.
Perfect, right? And as you can see, if I switch around the two events in like D and E, the probabilities are different. So it does matter like what order these go in. That number or the number of people that have the second event changes that bottom number. So the order does matter when we have that conditional probability line there. Okay. Any questions on example number 4? All right, I think I burned this into your brains. I think we're all good on this. So I think we're ready to move on to our next section. Oh. So new section means new set of guided notes. Let me pass this out. All right, and I'm going to be honest. I wrote out what I was going to talk about today here, but I am not used to teaching after being away for a while. So if I stumble through this, then that's okay. Okay. So we are starting a brand new section. It's called the central limit theorem. And if you talk to any statistician and you ask them what's the most important topic in statistics, or at least probability theory, they'll tell you that the central limit theorem is probably the most important thing in the entire world. So this is a very important section. It'll come up throughout the rest of the semester. We'll be talking about this theorem. So I want to make it like super important. And I want us to understand exactly what this theorem says. It's a little bit tricky to understand, but once you kind of get the idea of it, it becomes pretty easy to answer questions about. So what I want to do before we even start this theorem is I want to give you some notation. I don't know if I've talked about this yet, but this notation is going to become really important because I'm going to be talking about this throughout the rest of the semester. So let me give you some notation here. Okay, let's say I have a big population, right? And I take a sample out of it, right? So a sample is smaller than the population. It represents what the population is. Usually when we talk about a sample, we have a specific number of people we take out of the population, right? And usually we call that N. Okay, so usually N is like the sample size. Okay, so whenever I write N, that just means like the total number of things that are in the sample. Okay, now we've talked about mean and standard deviation before, but the symbols for them are actually different if we're talking about a population or if we're talking about a sample. Now, I've given you the symbols, but I didn't tell you that they were specific to the population. Does anyone remember the symbol for the mean?
Is it
Greek letter M or mu, right? Now, that's the symbol for the mean, but what I didn't tell you is it's really only the symbol for the mean if we're talking about the population, okay? So mu only really works if we're talking about the population. Anyone remember the symbol for standard deviation? Michael? Lowercase sigma, right? So I like to say a circle with a line on top, right? That's the Greek letter for S. And well, it represents the standard deviation, but it's very specific to the population. Okay. On the other hand, if we're talking about a sample, we're going to start using symbols to differentiate the mean from the mean of the sample from the mean of the population. So if we're talking about a sample, the mean of that is going to be this. It's going to be X with a bar over it. So lowercase x bar, that's going to represent the mean of a sample. And sample standard deviation, really easy. It's just S. Okay. So the way I like to go about this is if I'm talking about the population, that's where the Greek symbols are going to come out. If I'm using like a regular symbol, like not Greek, that's going to represent a sample. Okay. So let's kind of recall what we've been dealing with when we talked about samples before. I think like the very first day of class when I talked about samples, I said, okay, one way we can think about a sample is, let's say the population was a prism, like a rectangular prism, right? Okay, and let's say my drawing skills are somewhat okay. That wasn't too bad. That, honestly, yeah, that was pretty good. All right. So our population is the prism. Let me label the population. Okay. And then let's say from that population, a sample, an example of a sample would be taking what's called a cross section. Now this isn't going to be that great. Uh-oh. That's not too bad, right? A sample can be like kind of like a slice of the population. Like if I cut the population and just took out like a square out of the population, that could be a sample, right? Which I said was a cross section. Okay. Now, the thing about this is I said that this isn't a great representation of taking a sample from a population because populations can be of all different sizes and shapes. So a sample like doesn't always look like this, but let's just say we're in this situation, okay? Now, in a population, there's always going to be multiple samples I can take, right? I didn't have to slice in the middle. I could have taken a slice towards the front of the prism or towards the back of the prism. So in a population, there's a lot of different samples I could take. For example, if my population was like, I don't know, this class heights, right? So this class heights. I lined everyone up and I measured how tall everyone is, for example, okay? I could take, for example, a sample, let me write this in orange, a sample of size 2. And let me just use my symbols here. And my sample size would be 2, okay? Now, that sample is going to be a little bit different. For example, I could take, I don't know, Hunter's height and Emma's height, right? That would be a sample of size 2. I could also take, I don't know, Cass's height and Sarah's height. And that would be another sample of size 2, okay? Now, each of these different samples, well, they have a sample mean, right? I could add up Hunter and Emma's height divided by 2, and that would be a sample mean. I could also have the sample mean of Cass's height and Sarah's height. I could just take the average of those 2. So within each of these different samples, we have all these different sample means that I could take. Does that kind of make sense? Okay, so we basically have a big population mean, and then we have all the different samples that we could take. We have a bunch of samples here, and I have individual sample means for each of them. Okay, so let me see what I wrote here. in a population, we have multiple samples, multiple sample means. What we're gonna do now is we're gonna think about, okay, what if I take every possible sample? So I figured out what are all the combinations of two people from this class I can take. What if I took all their means and worked with the means? Maybe I could find the mean of the means, for example. Okay, so what we're gonna do is we're gonna introduce this word, the distribution of the sample means. Well, I kind of already know what the sample means mean, right? We know that if we take a sample, we can get the mean out of it. This is plural because in a population, we have multiple different samples, so we have multiple different means. But then we have this word, the distribution, right? Does anyone remember what the word distribution means?
Distribute, or, well, not that kind of distribute, but like the bell curve.
Yeah, okay. Like when I introduced distribution, I talked about the bell curve. That's an example of a distribution. And that's kind of it, right? When we talk about a distribution, we're doing stuff to kind of look at the overall shape of something, right? So for example, we could graph it and see what it looked like. Maybe it looks like that, right? So we're basically taking these sample means. We might like make a histogram out of it and see like where they come or how they're spread out. Is there a pattern to these means? What's going on with all the means in all the samples? Okay, so basically we're just trying to figure out how are the means spread out. Okay. All right, well, that wasn't too bad. I feel like I'm more prepared talking about this in the fall because in the spring, I'm just like recovering from spring break and I'm like trying to figure out what to say. But I think I did okay there. All right, let's flip our page over. Let's find an actual example of this. Okay, so what I'm gonna do here is, let's say we have a situation here, okay? We have a group of 6 people. I'm actually gonna draw them out, okay? So we got 6 people, they're standing in a line. Okay. And I'm gonna number these people, okay? So we got person number 1, we got person number 2, 3, 4, 5, 6. So that's their name, person 1, 2, 3, 4, 5, and 6. Okay, so basically I've created a population. I know that populations are normally really large, but in this situation, we have a population of just 6 people. So it's a very small population of people. Okay. Now, what I want to do is I want to take a sample of 2 people from that population. Remember, our sample size is n, right? So I want to take a sample of 2 people out of that population. And let's just say that every single person has an equal chance of being chosen. So I don't know, I choose their name out of a bucket or something. Okay. First of all, let's focus on the population first, and then we'll go into what the samples are. So if I wanted to figure out what the population mean was, maybe the first thing I would do is create a probability distribution out of these 6 people. Okay, so what I mean by that is I could list every single person in my population. 1, 2, 3, 4, 5, 6. These are just the names of the people. Okay. And along with this chart, I can put the probabilities that I choose each of the people, right? So I want to find the probability of choosing person 1 or choosing person 4 and so on. Okay. What do you think the probability that I choose person 1 is? 1 out of 6, right? Not just 1, but 1 out of 6, right? Because there's 6 people. They're equal. They're equally. Oh gosh, they have an equal chance of being chosen. There we go. So the probability of choosing them has to be 1/6, actually, for every single one of these people, right? So this is kind of like my creation of, okay, I know these are the probabilities of each of these people. If I wanted to find the population mean, let's go ahead and do that. The population mean. Well, we have some symbols to use. I know that the population mean is mu, right? Does anyone remember how to find the mean of a probability distribution? Has to do with multiplying down, and then adding across, right? So yes, basically, if you wanted to find the population mean of this, some review for a test in 2 weeks from now, you'd multiply down and add across. Right now, I am kind of too lazy to do that, so I just did it in my office. If you wanted to find the population mean, it'd be about 3.5. Okay. Now, what would be really mean for me to do is ask you how to find the standard deviation, which remember uses that chart. You have to like do, you have to square all the values and multiply them by the probabilities. We're not going to do that because I feel like that's just a little bit too hard here. But the standard deviation or sigma would be 1.708 if you did it, which we're not going to do because I don't feel like it. Okay. So we found the population mean, we found the population standard deviation. I'm going to do one more thing. I'm going to create a probability histogram, which remember is just writing all the X values on the X axis. We're not going to make it too fancy here, but the X values are just all the X axis values, right? So we got like 1, 2, 3, 4, 5, 6. And then the bars just go as high as each of the probabilities. So if I were to make this probability histogram, I know that the probability of person 1 is 1 out of 6. So that would be a bar for person 1. The probability for person 2 is also 1/6. So I guess that would be the same height, right? Person 3 would also be 1/6. Person 4, 1/6. Person 5, 1/6. Person 6, 1/6. So this is a very bland histogram. There's no shape to it. This is actually an example of something that we call uniform. Okay, which means it just has no shape. It's literally a flat histogram and that's it. So nothing really special happening here. Okay, this is definitely symmetrical. What was I going to say about this? Let me write this out. This is uniform. This is symmetrical. This is definitely not a normal distribution, right? It doesn't have that normal bell curve shape. But if you ask any statistician here, a statistician would actually tell you that this is approximately normal. Okay, so it's not normal, but it's approximately normal. It's close enough. Okay. Okay, now we'll keep that in mind. Let's forget about that and move on to the samples here. Okay. Now we have 6 people. I want to take 2 people as my sample. So my sample is of size 2. Does anyone know how many possible samples that there are? It's actually kind of a hard question. Gabriella. There's a little bit more than that. Why don't, okay, I actually find this hard to do. This is like a counting question. This is more of like a math major question. We do a lot of questions like this in like our higher level math classes. Now, I don't like formulas. I don't like figuring this out. So what I like to do is just brute force it. Let's figure out what all the samples are and just write them down. Let's do that. Okay. So let's say I wanted to figure out, okay, how many different samples are there possible? Well, an example of a sample could be like person number 6 and person number 5, right? That's a sample of size 2, right? Okay. Another sample could be, I don't know, person 6, person number 4, right? And person number 6 and person number 3. So we can continue creating samples like this. Before I go on, let's figure out what's possible here. If I choose a sample like person 5 and person 6, would I need to write down person 6 and number 5 and person number 5? No, because that's the same sample, right? If I pick Cass and Kayla, that's the same thing as Kayla and Cass, right? That doesn't change the sample. So these 2 things are equal, okay? And another thing that I want to point out is, let's say I choose person 6 and person number 6. Is that a sample of size 2? No. Right, I can't do, okay, Raven and Raven. That's not a sample of size 2, that's a sample of size 1, right? So that doesn't work, okay? So do you think maybe you could go through and write out all the different samples here? Yeah, I'm gonna give you like a minute to try to figure out, okay, what are all the different samples I could do here? And maybe that'll give us an idea of how many samples there actually are. How many samples did you get? 15. Everyone else get 15? Yeah, they actually, there are 15 samples here. So it's a little bit more than what we think here. I'm actually gonna write them out. So we had 6, 4, 6, 3, 6, 2, and 6, 1, right? Now I'm a little bit more like methodological. I don't know if that's a word. I don't know. But I like to write them out in like a pyramid. So 5, 4, 5, 3, 5, 2, 5, 1. Once I'm done all the samples with 5, we got 4, 3, we got 4 and 2, we got 4 and 1. And then after that, what we have 3 and 2, we got 3 and 1. And then finally, we got 2 and 1. And after that, we can't really make any more samples. So in total, there actually are 15 samples. Okay. Now, what we're going to do here is we're going to work with each of these samples on their own here. So if you flip our page over, I'm going to actually put you to work here. I kind of feel bad doing this, but I know you just wrote out all the samples on the last page. What I want to do is make it a little bit more like organized here. So what we're going to do is I'm just going to write out all the samples in each of these boxes. Okay. Now, keep in mind, you're probably not going to fill in all these boxes because I put more to kind of throw you off. But what I'm going to do is I'm going to write all the samples involving 6 up top. So we got 6 and 5. We got 6 and 4. We got 6 and 3, 6 and 2, 6 and 1. We got all the samples involving 5 here, 6 and 4, 5 and 4, 5 and 3, 5 and 2, 5 and 1. On the third row, we're going to write 4 and 3, 4 and 2, 4 and 1. On second to last row, we got 3 and 2 and 3 and 1. And on the very last row, we got sample 2, a sample with person number 2 and person number 1. Okay, so each of these cells kind of represent one of these samples, and we have 15 total. What I'm going to do is for each of these samples, well, we're interested in the sample mean, right? If we're interested in the distribution of the sample means, maybe we should figure out what those sample means are. Okay, so let's say I wanted to find the sample mean of the first cell. What would I do? So let's say I wanted to find the sample mean of 6 and 5. Well, how do you find the mean of 2 numbers? Perfect. Add them together, divide by 2, right? So the sample mean of the first cell is 5.5. Okay. And what we're going to do is we're going to do that for every single one of these samples. So what I'm going to have you do, yeah, I think we have a little bit of time. How about this? The left half of the class, or Cass and Over, why don't you find the sample mean of the first 2 rows? And then Alicia and to the door, you can find the sample mean of the last 3 rows. Okay, and then the last one I think was 1.5. So I think we're actually even seeing a pattern as we write it up here, right? So basically all I have are all the samples and all the sample means, and I don't think we're gonna get to the next thing here. So how about this? Next class, we're gonna figure out what the distribution of all our sample means are. We just found the sample means, now we're gonna find how they're spread out. And we'll find something interesting on Wednesday.